Hello everyone, welcome back. In this video, we'll be taking a look at integers and rational numbers. So, what are integers? If you notice from the previous videos that the natural numbers had a big problem with them. They didn't have any additive inverses. So all they had was 1. There was no way, sorry about that, we could get 0 by adding something which is in the integers. So there was something missing there. So we needed a better number system. Therefore, we defined the integers. So the integers are defined in such a way they are the union of the natural numbers with the union of the negative natural numbers with the union of 0. So now we have a set which kind of looks like this. So which is better than what we had before with the natural numbers. So because now we have an additive inverse and we have zeros and we have a 0 and we have additive inverses. So this number systems seems to be more complete, but there's still a problem. We do not have any multiplicative inverses or multiplicative neutrals. So for example, if we take 2, we do not have a multiplicative inverse for 2 in the natural numbers. The multiplicative inverse of 2 we know is half, but half isn't an integer because integers only have whole numbers in them, if you have noticed here. So we do not have multiplicative inverses in the integers. So therefore we need an even more complete number system. So therefore we build the rational numbers. Now, the rational numbers are any numbers that can be represented as a fraction m over n. So for example, 2 is a rational number because it can be represented as 2 by 1. 1 is a rational number because it can be represented as ratios as 1 is to 1. 8 over 3 is a rational number because it can be represented as ratios of 8 by 3. Therefore, all these any number that can be represented as a fraction is a as a fraction is a rational number. So this seems to be a more complete number system. So we can start doing our analysis on this. But if you have noticed, the rational numbers too have a bit of a problem with them because in the rational numbers is incomplete. It has gaps in them. So for example, if you take this as the rational number line, if we start here from 0, we go to 1, we go to 2, and between 1 and 2 we realize that a number line is incomplete because of the existence of root 2, which is equal to 1.4, and root 2 is not a rational number because root 2 cannot be expressed in the form of a fraction. So we realize that the rational number line has infinite millions and millions and trillions of holes in them. So we cannot start doing our calculus and analysis on such a weak number system which has holes in it. We need a more complete number system before we start doing our analysis on it. So therefore, the rational number also fails to meet our standards. So we go and build the real numbers. So before we do that, let's take a bit of a look at why root 2 cannot be expressed as a fraction and why root 2 is not a rational number. So basically root 2 is an irrational number. So let's do the proof of this. So we're gonna attack this by doing a proof by contradiction, because remember, proof by contradiction is a very useful proof technique. Whenever you're confused about a proof, try use proof by contradiction. So we're gonna assume that root 2 is a rational number. Remember, when we're doing proof by contradiction, we assume the opposite. So suppose for contradiction, we assume that root 2 is a rational number. So if root 2 is a rational number, that means it can be expressed in such a way as m over n. Now let's square both sides. We get m squared over n squared. Now remember, this m over n is in its reduced form. For example, m over and what do I mean by reduced form? That means it cannot be simplified any further. For example, 6 over 3, or let's take 6 over 8 is not in its reduced form. but 3 over 4 is in its reduced form. It cannot be simplified any further. So if it cannot be simplified any further, that means either the numerator and denominator are odd or even, or they're both odd, in such as this case. But if notice that if they're both even, if the numerator and denominator are both even, for example 2 by 4, then they can be reduced as they can both be divided by 2. So we're assuming that this m over n is in its reduced form, i.e. they're both, i.e. both or m and n are odd, or one of m or n is odd and the other one is even. So when you square this, you get 2 equals to m squared over n squared, which can be written as 2n squared equals to m squared. Now this means that m squared is even because we're multiplying n squared by an even number 2. So anything multiplied by 2, if 2 multiplied by 2, okay, let's take 2 multiplied by 6, and 6 is an even number, we get an even number, and 2 multiplied by a odd number, we get an even number also. So m square is even because it's being multiplied by 2, because m square is equal to 2n square and 2n square is even. This shows m square is even. So if m square is even, then m in turn is also even, because the only way we get even is if even times even is equal to even. That's the only way we can get a even. So if this is m square, then m has to be even, because the only way we can get a m square which is even is if we multiply two even numbers together. So this shows m is also even. So m in turn can be expressed in the form as 2 over 2 times k, because since m is a even number, m can be also expressed as an even m is even number, so it can be expressed as a even number multiplied by 2. So for example, if m is 8, it can be expressed as 2 by 4. If m is 6, it can be multiplied as 2 by 3. So this is what we're doing. We're taking m is the same as 2 by k, because m is even and 2 by k is even, which guarantees us that m is even. Since m is even, we're just dividing it by 2. So we're expressing as m as 2 by k. Now we can now write this as 2n squared is equal to m squared, and m is 2k, so 2n squared can also be written as 2k the whole square, which it can be written as 2n squared equals to 4k squared. If we simplify this, we get n squared equals to 2k squared. Now this shows that n squared is also even, since a number k squared is being multiplied by 2, this shows n squared is also even. And since n squared is even, just as the argument we did before, n is also even. So we get that n is even and m is even, but this is contradiction. This is a strange thing which is happening. This is strange. This contradicts, because we just assumed that m over n is in its reduced form. That means either one of both of them cannot be even. If both of them are even, then they can both be divided by 2 to get an even simpler form, to get an even simpler reduced form. But we just assume that m over n is in its reduced form. It cannot be reduced further. So but we are getting m is even and n is even, which means they can be reduced. So this contradicts. Therefore our initial assumption that root 2 is rational is wrong. Therefore since our assumption is wrong, this shows root 2 is irrational. That means it is not rational, and it cannot be expressed in terms of a fraction. So we've just noticed that the rational number line has several holes in it. For example, it does not contain root 2, which is a irrational. Root 2 is not a rational, so it is not in the rational number line. So just like that, there are millions of irrational numbers which do not fit in, which create holes in the rational number line. For example, pi is a rational number, the special number e is I'm sorry, pi is an irrational number. The special number e is also an irrational number. So we get that there are millions of holes in the rational number line. Therefore, the rational number line is not complete. We need a better number system to do our analysis on. So we'll see what to do about that next video. Hope you guys enjoyed this video. See you next time.